A very warm welcome to one and all. I am B. Rohan, a student of ECED, and me, along with my fellow students Sai Manohar and Ramana, have done our final year project in the domain of VLSI. And our project is called the implementation of carry lookup adder with 2-bit approximate adder. We have successfully published our paper in the second International Conference on Applied Artificial Intelligence and Computing. And all of this has been possible under the esteemed guidance of Dr. K. Jamal sir, who is a professor at the Department of Electronics and Communication Engineering in Gokaraja Rangaraju Institute of Engineering and Technology, Hyderabad. So coming to our project, as the name suggests, it is the implementation of carry lookup adder with a 2-bit approximate adder. Here we are working with the already existing carry lookup adder and working on few existing aspects such as power consumption, complexity of the circuit, area consumption, and working on these aspects and making a better outcome by working on the already existing carry lookup adder. So in this project, we present a new design for an already existing carry lookup adder uh, by addressing the issues of area and power consumption along with the circuit's complexity. So these are the three main attributes we are going to be concentrating on. That is the area and power consumption, and along with the circuit's complexity. By reducing all these three, we can make the already existing carry lookup adder more efficient. So in order to achieve this, we incorporate an approximate adder. Approximate adder is a combination of two parts, one that provides precise calculations and the other that provides less accurate, that is inaccurate calculations, with the approximate portion designed in a way that minimizes the circuit's area and power consumption. So using an approximate adder reduces the area and power consumption. That is why we have brought the approximate adder into play. And then our proposed design uses a 2-bit approximate adder in an I-bit carry lookup adder, and its effectiveness was evaluated by comparing it with an accurate CLA in terms of area and power consumption. So the already existing carry lookup adder is compared with carry lookup adder with a 2-bit approximate adder, which we are going to be implementing in this project, and the results of area and power consumption along with the circuit's complexity is compared in both uh, the adders, and the efficiency is determined. So going down here, adders which are commonly used in arithmetic and logic units can also perform other power consuming operations such as subtraction, multiplication, and division, making the reduction of area and power consumption an important and challenging task. So approximate n-bit adders, as we can see, approximate n-bit adders, we use m-bit approximate adder in the least significant part and n minus m-bit accurate adder in the most significant part. So it consists of an LSP and an MSP. Coming down, why do we need approximate adders? Approximate adders are very important where exact calculations are not required. Let us understand this by taking an example of a portrait photograph. In a portrait photograph, the person in the photo is more concentrated and all the background views are blurred. So this is where the approximate computation comes into play, because since we don't really need the clarity of the background, we can approximate all the pixels available in the background since we have to blur them anyway. So this is a good example for understanding where we need approximate computation. And further, these are the literature surveys, all the papers we have used in this. So coming to the existing method of a carry lookup adder, a carry lookup adder is used for performing binary addition by using the concepts of carry, generate, and carry propagate. A carry lookup adder operates by generating two bits called carry lookup, and carry lookup adder operates by generating two bits called carry propagate and carry generate, which are represented by Pi and Gi, as we can see in the circuit. This is the carry propagate and this is the carry generate. The carry propagate bit gets propagated to the next stage, and the carry generate bit is used for generating the output carry bit, and this is independent of the input carry bit. So this is how the existing method looks like. Coming down to the carry generate and carry propagate, to be more specific, there is a specific mathematical expression that describes how carry generation and carry propagation are implemented. Carry generation is uh, the output of AND operation between two inputs, and carry propagation is an output of XOR operation between two inputs. Here, as we can see, carry generation is A and B. Let us consider A and B as two inputs. So carry generate would be A and B, and carry propagate would be A XOR B. The carrying output of CLA is provided by this expression, and substituting the values of carry generate and propagate in this expression, we come down with the result of this expression. An increase in the size of area of a carry lookup adder results in higher delay and power consumption of the CLA. So yes, and coming down to the disadvantages of the existing method, as we have already discussed, as I've already mentioned, that we are going to be discussing about area, power consumption, complexity, and delay. So the area consumption is high, energy consumption is high, delay increases as the computation time of output increases. These are all the disadvantages present in the already existing carry lookup adder. So in order to overcome these disadvantages, we are going to be proposing a method. So wherein we are going to be working on the already existing carry lookup adder and making certain changes to it by improving the area, power consumption, and delay and complexity of the circuit. So coming now, this methodology suggests using a specific design approach. So this is the 2-bit approximate adder we are going to be using and inculcating in the existing carry lookup adder. The goal is to create a function for the least significant bits of the least significant section that is not dependent on any data and can provide an approximate output without generating or using carry over sum calculation. So as we can see in this truth table, instead of using two full adders for adding j-2 and j-1 bit separately, it is possible to add both the inputs simultaneously by using a 2-bit approximate adder, which reduces the area and power consumption. Since we are not using two circuits and we are using only one circuit, the area and power consumption ultimately get reduced. As you can see in the truth table, where the input bits are given to a 2-bit approximate adder, it yields certain outputs here. So these output bits are same as that of the output yielded when the same input bits are given to two full adders. But here we are giving it to a 2-bit approximate adder. There are certain cases where a carry 1 is generated when certain input bits are given to two full adders. They are marked in red here. As you can see, all these red marked outputs are the cases where carry 1 is generated when certain input bits are given to two full adders. The remaining I minus j bits are given the traditional carry lookup adder, which carries out the traditional addition and gives the result. Carry lookup adder, there is a slight divergence in the result when considering factors such as area and energy usage. It becomes apparent that the approximate carry lookup adder exists in a lower area. Then we can come down. We can see this the circuit diagram of a carry lookup adder. Now, since we've discussed about the existing carry lookup adder and 2-bit approximate adder, and now they were implementing both of them in the same circuit. So here, as we've talked about approximation, as you can see here, all default ones are given. You can take either zeros or ones. We have used this in order to approximate, which will ultimately reduce the area and power consumption and also the complexity of the circuit. And yeah, this is a representation of the 2-bit approximate adder using the gates. And as you can see, this is the example of the accurate carry lookup adder, and it yields a result of 74388. And coming down to the approximate carry lookup adder, which we have implemented, the result comes out to a 74367. So the advantages of our implemented carry lookup adder with a 2-bit approximate adder, as we have discussed above, we can see that the area consumption is optimized as we are giving default zeros or ones, which will further reduce the area. And then since the area is reduced, the energy consumption is also reduced, and further the delay will be reduced. And coming to applications, the applications of these include digital signal processors, image processing, video encoding, video decoding. As I've already given an example of a portrait photo, which is an example of an application in the image processing, wherein the background can be blurred and there the approximate computations can be used. So we have used Vivado Xilinx tool in order to compare the uh, the area and power consumption and the number of LUTs used along with the input-output devices. So these are the schematic. This is a schematic diagram of carry lookup adder, traditional carry lookup adder. Here, as we can see, the LUTs used in the traditional carry lookup adder is 29. Input-output devices used are 50, and the total power consumption is 11.492 watts in a traditional carry lookup adder. Now, coming down to the carry lookup adder with approximate adder, which we have implemented in this, we have proposed in this project. This is the schematic diagram, and coming down to the number of LUTs used, it's 12, wherein here the LUTs used are 29, and number of input-output devices used are 38, and here in the traditional carry lookup adder, the number of input-output devices used are 50. So as you can see, there is a significant difference in the number of LUTs used and input-output devices used. And the power consumption is also lesser, 6.644 watts from 11 watts, which is a significant difference. Yeah, as you can see, for a better understanding, we have it all on the same page. So a conventional CLA uses 29 LUTs, whereas a proposed method uses 12 LUTs. And the input-output devices use a 50, and here the input-output devices used a 38. And there's also a significant difference in the power consumption. So we can say that the proposed method, whatever we have given, improves the area, power consumption, and delay along with the circuit's complexity. So yes, thank you everyone.